Yeah, so my name is Andreas. Today I'm going to present OptiBasePen. And so OptiBasePen is a pen input device that works on passive surfaces. So you can do any task that you would normally do with a digital pen, but you're not confined to a tablet or drawing tablet surface. So you can, for instance, annotate documents, but you can also use it for sketching. And also, to a certain extent, you can also use it for input slightly above or like above the surface. So the device can also sense the vertical position or the distance to the surface. And before I get into any more detail, I want to briefly talk about previous approaches and the problem in general. So conventionally, when we think of digital pen input, we think like drawing tablets, like specialized sensing surfaces that can sense the pen position, or tablet and stylus interaction, like with the Apple Pencil Pro, for instance, to use tablet devices and then capacitive screens for pen input. And also in research, people started to sort of investigate how can we sort of leave those active sensing surfaces and use basically any like flat surface in the environment for pen input. And so, for instance, TipTrack is using an infrared LED at the pen tip to track the pen. And the problem here, however, is while it's very accurate and you get the absolute pen position, like you know exactly where along the table the pen is located, you need quite a sophisticated setup. So you need high-resolution cameras, high-frequency cameras, and which really limits the mobility of the whole setup. So it's not really used for mobile use. Like instead, it's for like high-precision projection mapping interactions. And then there's DeltaPen, which is basically only using relative sensing. So you have the pen which is sensing its own translation and rotation and doesn't need any like external sensors. And it's doing that by having the sensors included, like 2 optical flow sensors in the tip, which then makes it useful for mobile use, but because it's completely relative, you don't really have any frame of reference whatsoever. So you have to deal with drift, for instance, when it comes to the rotation and so on. And so the question here is, like, can we somehow combine or find a good trade-off where we combine the advantages of absolute pen tracking and of relative pen tracking, so to enable mobility, and at the same time avoid issues like drift, for instance. And so that's what the Base+Pen concept is about. So here the idea is that, as the name suggests, so you have a base and you have a pen, and the pen itself is very simple. It simply has like one LED, and then the base has 2 object trackers, which are basically infrared cameras, and from a close range they can pretty easily detect where the pen is. And then the base itself has a mouse sensor included or integrated, so that means it can sense its own relative movement, and then in the end we just add those two positions up, and then with the vertical position we can also detect surface contact to then use it for like annotating, drawing, and so on. And so to like briefly formalize all of this, so basically we are combining relative and absolute input. So the pen tip position is absolute within the frame of reference of the base, and the base itself is relative, and that's what the whole like Base+Pen concept is basically about. And next we of course have a reference implementation, so I want to briefly go through our hardware and our software approach. So the hardware of the pen is quite simple. Again, it only includes like a single LED, and the rest is completely passive, and the electronics are mostly in the base. So we have a microcontroller, we have the mouse sensor, and then most interestingly, the object tracking cameras, which are 2 PAJ sensors. And so what they see is basically this. So here the frame rate, of course, is very low because when sending raw images, it reduces the frame rate considerably. So normally they sense at like 200 hertz, but here this is just for illustration to kind of see what the cameras would, or one of the cameras is seeing. And so briefly about the pipeline. So we have different components. So we have the microcontroller unit, of course, in the middle, and then we have the our software, of course, we have the two sensing components, and then everything is ending up in the application. So let's quickly go through it. So there's a simple clock in the microcontroller, and every 5 milliseconds, so at 200 hertz, it's pulling the data from the two sensors. And then if there's motion from the mouse sensor, it's forwarding that motion to the software, and the base position is updated. And then similarly, it's forwarding the object positions or the blobs that those sensors are detecting also to the software. And again, to reiterate, so the sensors themselves have integrated blob detection, so at 200 hertz, we directly get the blob positions. So therefore, it's really nice for like low power operation. And then in the end, we fuse it all together into one cursor and send it to the application. So we also conducted a technical evaluation to like primarily or like specifically focusing on the cameras in our setup. So what we did was we took a Wacom tablet as a ground truth. So, and we just simply attached an LED to that Wacom pen, and so the rest of the device is the same. And to briefly glance over the results, of course there are a lot more details in the paper. So here we can see 3 different plots overlaid. So the Wacom is the gray one, the gray line in the background. And then the raw samples are the orange dots here, so we can see that they're somewhat dancing around a little bit. And then we also have a filtering approach, which I don't have time to go into right now, but of course you can read it up in the paper, and that kind of smoothes out those somewhat shaky samples. And then also to give you some numbers, or at least maybe the most important ones, the mean absolute error, like compared to the Wacom ground truth, is 1.87 millimeters for the raw samples, and then when smoothing, it reduces slightly to 1.69 millimeters. And we also measured other things like latency, so I encourage you to read the paper to read about more results. And so let's briefly talk about some use cases, or like the primary use cases of the pen that we implemented in this iteration. So first, of course, there's mouse input. And so what you can see here, and for some reason the frame rate is a bit low, but I hope you still get the idea. You can simply annotate documents, as I mentioned before, but also the mouse or the device can be configured to act as a Bluetooth low energy mouse. So the base can also be operated in a wireless mode, and then we simply forward like the mouse events to the operating system. And again, for some reason, PowerPoint is running a bit slowly right now, so the frame rate is a bit shaky, so I apologize for that. And yeah, so basically you can use it as an ordinary mouse as well. But of course, since it's a digital pen, you probably mostly want to use it for things like sketching and painting. So here we have a very simple painting app where you can simply select a color and then draw different strokes. And then, of course, you can use that to sketch some simple shapes, as you can see here. And then there's also interaction above the surface. So since the cameras are like, we triangulate in 3D, of course, so everything close range. So we can sort of also estimate the distance of the pen compared to the surface. And so that means, so the left and right and up-down movement is working as before, and then moving away from the surface works as well. And then we also have a pressure sensor at the pen so that you can grab objects in mid-air, for instance. Which also means you can, for instance, do things like manipulating articulated characters, like the one here. And then, yeah, so that's sort of like for interaction right above the surface. But actually, you can also combine the two. So if you can also, without having explicit mode switch, kind of seamlessly switch between interacting on the surface and above the surface. So here's a very simple example. So as before, you can use the app for painting, but also when like kind of raising the pen in the air, you instead get into some sort of like meta mode where you can then move around widgets, and then as soon as you go down with the pen again, you just use it again for just ordinary painting. And so that in itself also points to some future questions about like, what does it mean to, for instance, do like close range mid-air pen input interaction, which is something sort of we started to explore in this paper, but of course it's also very interesting to investigate in the future, which also brings us to future work because there are like many open questions and many things that can be improved with the reference implementation, with the concept and so on. So for instance, we could use higher resolution cameras. So right now, one limiting factor is really the resolution of the cameras, which is like 98 by 98. And of course, we can still use those cameras because it's very close range. That means we can use low power, low resolution cameras, but still having slightly higher resolution would of course be nice. And then also investigate ergonomics and optimizing ergonomics, like how do we best kind of create a shape of the base so that it's also can be used ergonomically. And then also using alternative close range sensing methods. So optical sensing, of course, works long range and close range, and then again, using close range means we can use a low resolution, but then there are also other sensing methods which might work particularly well when used in a close range mode, like for instance, magnetic sensing or radio frequency, which could then be integrated in the base instead of the cameras, for instance. And then also, of course, right now the pen is mostly passive, like there's only one LED, which means like the whole pen is still, there's lots of space to just add other components. As for instance, there could be pressure sensing at the tip. There could also be a capacitive tip so that you can use it like on a surface, on your tablet, but then maybe for like other modes or other interactions, you could instead use the base and right next to your tablet to like do some sort of like meta operations, or the other way around. So like the switch in between on the screen and off screen, for instance, might also be interesting, or like all without switching the device, like using the same pen. And then of course also actuators, for instance, for haptic feedback. Yeah, so to quickly conclude, so what we presented here is the concept of Base+Pen, so which is all about combining relative motion sensing with close range pen tracking. And then also there's the first reference implementation of this concept, which is OptiBasePen. And yeah, so with that I would like to conclude, and thank you for your attention, and I'm of course open for questions.
Yeah, thank you for a great talk. I'm Taejun from KAIST. If I understood correctly, the cameras attached to the base are taking the RGB pixels to process the absolute reference frame. So which was the point that made me curious about the stability over different lighting conditions. It's like, is there any like testing testing result or your expectation on those matters?
Yeah, so that's a really great point. So we did not test it like outdoors in any way, so it might be that it's very sensitive to different light conditions. Mm-hmm. So of course you can always use different infrared filters. So everything is in the infrared range. So to a certain degree, also the built-in filters are like mitigating this a little bit. But in the end, if you want to have it like fully stable, then we would need to look into like other techniques or approaches for mitigating this. So for instance, there's previous work on like turning on and off the LED like in the same frequency as the cameras, and then you just, instead of looking at the absolute values, like you just look at the differences between frames, which makes it a lot more stable in terms of like light conditions, because even though they have the same intensity as maybe the environment, you see the deltas in the frames, which kind of like it halves the frame rate, so from 200 to 100. But at the same time, it would then make it probably, so like it's also actually a good point for future research, makes it much less susceptible to different light conditions and or like usage in bright environments.
Yeah, thank you very much.
Thanks.
Hello, Sunjun Kim from Digis, Korea. So thanks for the nice work. What I want to comment is that your mouse sensor is not detecting the rotational components of the reference frame. So the any kind of the error from the rotation of the wrist will be accumulated to the reference frame in the longitudinal manner. So actually, he, Byung-Ju, have an interesting work to compensate that rotational component by using the 2-mouth sensor. So please check his work if you are interested.
That's also a great point. So yeah, like in general, like detecting like compensating for the rotation. I mean, there are different approaches. Like for instance, you could have like a reference light source in the background or something, so that the cameras not only pick up the blob of the pen, but also maybe some reference in the background, so that every once in a while they can kind of readjust so that they know their orientation. That's, for instance, one approach. But again, of course, like using a second mouse sensor would also be very interesting for like compensating at least like relative rotations. So yeah, it's an interesting problem.
Very quick question. Jackie Young from Skywalk, and then I'm not sure if you mentioned it, I might have missed it. You mentioned the position accuracy. Did you mention the contact detection accuracy of the?
No, unfortunately we did not. So that one, yeah, so.
Because I figured maybe using the position to detect contact might not be very accurate, especially if my tip is close to the surface.
Yeah, so the reason we did not measure this explicitly is because it depends on like some factors which are like outside the actual like camera or like setup performance. Like it depends also on how accurate the 3D print of the pen is, and so like how far away the LED is actually from the surface.
Right.
So there were like a few factors which were hard to control. So I mean, admittedly, we could still have provided some numbers even with that very, very specific setup. But because it had so many like parameters, we kind of focused more on the 2D position, which is like kind of like the main focus of everything. Yeah. But of course, also in the future, we need like also better ways of detecting surface contact. Like for instance,
the IMU on the pen would help a lot.
So, sorry. We do got to keep things moving here. So thank you guys again.